every time. Let's see. Yep. Test, test, test. Looks like we're using the correct microphone. Boom. So, yes. So here we are again. It's always such a pleasure. Good morning, fancy meat computers. I apologize for having to do the stream online again, and I actually do have your midterms at my physical location, most of them anyway. Celine was going to be bringing some more. We'll just have to distribute them next week. Possibly it'll have to be... Am I still coming through? I'm getting no data. Test, test, test. Okay. Probably next Friday it will have to be, because that's the only class where, like, there's no class after our class in the room, and also I have no class after our class, so that's like the only viable time to be able to distribute the tests. So there you go. Also, if you haven't heard the word hummingbird, my convocation ceremony, during which I will be made officially and finally into a doctor, that's happening on Friday in the morning, and is going to mean that I'm canceling classes Friday morning, including this one. So this will be our last lecture of the week, as it were. Good. So yeah, I do feel a bit of a cold coming on myself, but you know, I'm quite sure that I'm contagious. The house is now currently a pile of slime. So yeah. Do we get our marks at the same time that we get the test? No, the marks should be coming out soon. I had a couple of TAs who forgot that they had to add the marks to Avenue, and they are now, I think, well, I'm not going to check Slack on stream. No. Get out of here, you. There we go. They just need to add the marks from the website, or from the offline gradebook, and then everything will be fine. I was watching the pre-recorded lecture and I saw ads littered throughout the video. Can I turn it off? No, that's your punishment for not coming to class. I worked very hard to get to the point where I could put ads on my videos. If you don't like ads that strongly, then I might recommend a browser with built-in ad blocking features like Brave. Our tutorial's running this week. Yes, tutorials are running this week. Why? Did you show up for a tutorial and nobody was there or something? Anyway, so getting into our lecture for today, we've been talking about graph algorithms. We've been talking most particularly about the depth-first search and breadth-first search, DFS and BFS, which is probably easier to say than breadth, but there you go. So, it would be nice to sort of end on this particular summary slide, actually. You just heard maybe they weren't. Well, I would say that if there's anybody in the crowd who's participating in these nasty rumors that there are no tutorials this week, I must ask you to cease and desist. This week is normal, and there's nothing happening next week. Everything's going to be fine. Everything's going to be running as normal. So, no, tutorials are running this week. And tutorials will be running next week. And every week after that. Whether there are TAs or not. What? There's no possibility of no TAs next week? What am I talking about? Strike action? Never heard of it. Anyway. So, the depth first search and breadth first search. Both of these guys are fundamental algorithms for searching graphs. In both, we put the source vertex on the data structure, then perform the following steps until the data structure is empty. Take the next vertex v from the data structure and mark it. Put onto the data structure all unmarked vertices that are adjacent to v. That is to say, we NQ all of the unmarked vertices adjacent to the next vertex. The question becomes, what type of queue are we using to store these vertex references? In the case of the depth first search, that's going to be a stack. The most recently added vertex is the one that you process first. This results in depth first search. With respect to the breadth first search, as has been already spoken about, putting things in a FIFO queue results in searching things layer by layer. Layer by layer. Strike is canceled? No, I'm making a joke. The strike is not canceled. I haven't heard anything about the strike. Actually, I should probably check my email to see if there is. I was making a joke because, like, basically, the direction from the university is that instructors shouldn't talk to anyone about the strike. We shouldn't acknowledge that the strike is happening or anything. This is like what we've been told to say. So, so I was in my overly sarcastic way poking fun at the university's manner in which they've decided to handle things, by ignoring the fact, or asking us to ignore the fact that the strike is looming and imminent, at least with respect to, you guys. There's been a lot of attempts to manage the narrative, shall we say. So, what was I? I had a point. That's backwards. Yes. So, the ultimate result of the breadth first search, the order in which it examines the vertices, because we are always adding new vertices that are found to the end of the queue, and not adding ones that are sort of already marked and should be inside of your own, like, any node inside the distance to zone will not queue anything else that's inside that zone. So the queue itself will have this interesting property that it will essentially be sorted by distance, distance to the source node. So no matter where you are in the algorithm, you're always going to be a number that's higher in the queue is always going to have a lesser distance to the source node than a number further down in the queue. That's just always going to be the case. And interestingly, always no more than one more step away. You don't get, like if you're currently processing the nodes of distance 7, you will be filling up the queue with nodes of distance 8, but no nodes of distance 9 will enter the queue until you start processing nodes of distance 8. And because all of the 8s are after the 7s, that won't happen until all of the nodes of distance 7 have been processed. So that's kind of how breadth-first search goes about it. In any connected graph G, breadth-first search computes shortest paths from S to all other vertices in time proportional to the number of edges plus the number of vertices. So you remember, I hope, way back at the beginning of the course when we were talking about worst-case runtime scenarios, right? And we were talking about big O and big omega and all of those fun guys. We had a slide briefly saying that big O notation can have multiple variables, right? This would be one of those situations in which the time complexity of the algorithm is based on 2 variables. So, because like the sort of native question that you like the question that's like native to the data structure is what counts as size now that we're talking about graphs, right? You might it might be intuitive to think that the number of nodes or the number of vertices is the same as the complexity of the graph. And certainly, the more nodes a graph contains, the more complex it is. That's absolutely the case. However, a great deal of that complexity is also encoded in the edges. So if you had a graph, with a million nodes, but no edges, the complexity of, the complexity of something like breadth-first search or depth-first search would be constant, right? We require edges to follow. So the number of edges, that is to say the degree of each vertex, also has an impact on the amount of runtime it takes to process a graph algorithm. Good. So, the difference between breadth-first and depth-first search lead to completely different views of the graph, even though all the vertices and edges connected to the source are examined no matter what rule is used. So let's speak briefly then about connected components. If you cast your mind way back to September, when we were talking about the union find algorithm, recall that we had this concept of connectedness reasonably well defined, actually more precisely defined than we've defined it so far here. Whether a vertex is connected to another vertex means that we have established an equivalence relation between these 2 vertices. First, equivalence relations are defined by the following 3 properties. Number 1, the property of connectedness must be reflexive. So any node or vertex must be considered to be connected to itself. connectedness is symmetric. So if V is connected to W, then W is connected to V. If 2 is connected to 0, then 0 is connected to 2. This, incidentally, is something that we will dispense with when we start talking about directed graphs. The symmetricality does not necessarily hold under such conditions. And transitivity. If V is connected to W and W is connected to X, then V is connected to X. So if 5 is connected to 4 and 4 is connected to 6, then we consider 5 to also be connected to 6. Connection really is defined as the existence of a path between two nodes, regardless how many nodes it must pass through. Yes. Given connected components, we can answer queries in constant time using union find. Fine. A connected component is a maximal set of connected vertices. So what does it mean to say a maximal set? It means that there are no additional vertices satisfying the property which are not in the set of connected components. Right? If you, for example, if you were to leave 1 out, then this gray blob is no longer a connected component, right? Because all things which are connected to the connected component must be included in the set that you are considering in order for you to call that set a connected component. Good. Any questions? Give me a thumbs up if you're having no trouble. Cool. So, excellent. So, let's now talk about how one would go about using our existing DFS and BFS algorithms in order to determine connection between connected components, to find in some way what the connected components are inside of a graph. So, our goal is to partition vertices into connected components. Partitioning means here just kind of identifying it. We're not like physically removing them from the data structure or anything like that. That would be silly. So, step 1. Initialize all vertices V as unmarked, which is what you do anyways. For each unmarked vertex V, run depth first search to identify all vertices discovered as a part of that same component. So, this is how you go about it. Let's see here. Oh. Huh. Okay. All right, this is going to have to be a demonstration then. Because I'm sorry, I haven't had the time to revise these, or I would have put the little arrows in. Tools. Review. F6. There we go. All right. There we go. All right. So, the first thing that you do, right? We are trying to partition, we're trying to find the different components that each of these guys belong to, right? So, the first thing we do is we check out item number 1. Can I just circle? There we go. We'll check out item number 1. All right. So we select, therefore, there we go. Hotkeys, my friends, hotkeys. So 0 will be our source, right? Now, the order in which this, like, I don't have the node adjacency array given to me here. So I'm just going to wing it. I'm just going to do a depth first search. Going like, let's do clockwise. Clockwise sounds fun. So, clockwise would be here. So, we've got 0. So, it's going to work out anyway. But, so, we mark this, right? We mark 6. 6 travels to 4. We mark 4. 4 travels to 5. We mark 5. 5 travels to 3. We mark 3. Okay. 3 is a dead end, so backtrack, 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 backtracks. Backtracks all the way back to the top. 2. Right? Then 1. And there you go. So all of these guys will be marked 0. Now, it's very important to note, in this particular example, these guys are basically already partitioned with respect to their node numbers. This is not something that you can assume when you've got like a regular, you know, when you're doing this on a more general graph, you can't just assume that the that all of these components will just nicely be adjacent numbers as well, right? You might have them scattered throughout the ID. Like these guys might be scattered around, and you might have to do more with them. But anyway, so in a similar manner, we now look for the next connected component. So we trace down the marked array, find the first item that's not marked, and say, okay, that's our new source. Right? So we perform the depth first search. 7 finds 8. That's all she wrote. So these two will be they'll have the next identifier. Next, we scan the marked array again, looking for the first unmarked thing. We make that our source. So now we're looking at 9. 9 finds 10. 10. Oh, and 9 is also checked off. 9 finds 12. And 9 finds 11. Oh, wait, no. 12 would find 11. Pardon me. Yeah, 12 finds 11. Boom, boom. And then these 4 components, those end up being 2. Does that make sense? So, using the depth first search, we have been able to reproduce the ID array that we had during very early implementations of the union find algorithm. Right? This would be quick find, I think. So there you go. Ugh, I really am actually coming down with something. Good. So, proposition. Depth first search using pre-processing space and time proportional to V plus E support constant time connectivity queries in a graph. So, So essentially, once you have run the depth first search and generated the ID array, to determine whether or not two elements are connected, all you have to do is look them up in the ID array and see if they return the same value. If they do, they're connected. Bing, bang, boom. Constant time connection. Proof is immediate from code. Each adjacency list entry is examined exactly once, and there are 2 such entries, 2 for each edge. Instance methods examine or return 1 or 2 instance variables. If you'll excuse me for just a moment, I need to go get a Kleenex. It's going to be terrible listening to the last 20 minutes of this, 25 minutes of this, last half of this with me snuffling the whole time. So, good. So, in theory, depth first search is faster than union find because it provides a constant time guarantee, which union find does not. In practice, however, the difference is negligible, and union find is faster because it does not have to build a full representation of the graph. More importantly, union find is an online algorithm. That is, we can check whether 2 vertices are connected in near constant time at any point, even while adding edges, whereas depth first search must first pre-process the graph. Therefore, we prefer union find when determining connectivity is the only task, or when we have a large number of queries intermixed with edge insertions. But we may find the depth first search solution more appropriate for use in a graph ADT, because it makes efficient use of existing infrastructure. So basically, the union find is specialized specifically for determining connectivity, right? The data structure is maintained in such a manner that connectivity is always obvious from it. This is opposed to the depth first search, which, while it pre-processes everything and finds everything, it sets things up so that you can look things up very quickly. If the graph changes, then you have to rerun all of the depth first searches each time the graph changes, and that is a much longer process than just maintaining union find, right? So it depends on the application. Can I explain how depth first search is constant time? There's a loop, so I'm a bit confused. So depth first search itself is not a constant time algorithm. If you use the depth first search to populate the ID array so that all of the connected components now have the same ID, the same way that we were doing with union find, then this access is constant time. So we have the complexity of depth first search, which is, roughly speaking, big O E plus V, right? We run that as a pre-processing step, and then when we want to determine connection can be determined in constant time because the ID array has been already populated. But it's kind of cheating because that means that you have to have it pre-processed in order to access it in constant time. And if it changes, that means you have to reprocess it. Does that answer your question? If there are any other questions, please throw those into the chat, and I will bring up the next set of slides. Wow, that didn't take long at all. Okay, so, if it creates the same ID array as quick find, why does union find not provide the same guarantee constant time? Well, could I post these slides? Yes, I can do that, yes. Let me just post these slides very quickly. Sounds like somebody had a bit of a tumble out there. Okay. The lecture slides are now visible. Topic 11, directed graphs. But to answer your question about union find, let me just, let's just take a look, shall we? Let's remind ourselves. So, yeah. So, quick find, right? Yes. Quick find is, of course, the same operation, right? When we use the depth first search to construct the ID array, that ID array can be queried in the same manner, essentially, as the it can be queried in the same manner and also yields constant time. Quick find also yields constant time connectedness access, right? But of course, if you recall, actually performing union over this data structure causes you to have to trace through the entire array, making it linear on the number of nodes. So that's why we go to the trouble of quick union, weighted quick union with path compression in order to speed up that process. Remember, so this is a better implementation with respect to quick union, but it's also a less, the find operation itself, again, becomes near you have to trace through a tree in order to do it. If you're using path compression, of course, you can flatten that quite considerably. So, you know, you can get to near constant time most of the time if you're using path compression, because there's no limit on the number of children that any parent can have. So, yeah, in general, I would consider union find to be a better algorithm for the purposes of determining connectedness. The question is, do you have a graph anyways? And if you have a graph anyways, do you just, if you have a graph anyways, and you're trying to determine connectedness in a graph, and you're not, like, willing to sacrifice the structure of the graph itself, then depth first search is a good way of going about it. So there you go. I want to just do, like, a very quick aside, because I've had graphs, like, in my life lately. One of the things that I sometimes do in the evening is I play video games. And I found recently that there's an open source re-implementation of a game from the 90s called Masters of Orion, which is now... Yeah, this is the game. It's completely free if anybody wants to play it. But I just wanted to, like, show you what this game looks like, right? And, like, that is a graph, right? Like, you've got these nodes in this graph, which is, like, the galaxy, and each of these nodes may or may not have planets, which you can colonize with your space guys. And it's a game of galactic conquest, and you have like spaceships also located at star systems. But, like, when the AI is, like, sending spaceships to attack you, what do you think they're using? What algorithm do you think they're using to find, a convenient path through the network to obtain your location? Do you think it might be something like a breadth first search? Yes, it's So yeah. Anyway. So, oh, we've already talked about union find. Get out of here, you. Don't save. Discard. There we go. All right. All right. Directed graphs. So, undirected graphs, right? We don't care about arrows. In directed graphs, edges are one way, right? Directed graphs are also sometimes called digraphs. Edges are one way. The pair of vertices that defines each edge is an ordered pair that specifies a one-way adjacency, rather than being an unordered pair that goes either direction. The in degree of a vertex in a digraph is the number of directed edges that point to that vertex. The out degree of a vertex is the number of directed edges that emanate from that vertex. That's some mighty fancy talk there, emanating from the vertex. Arrows in degree. Number of arrows out degree. Very simple. Makes sense? So you can see in this guy, we've got a directed path from 0 to 2 along the edges of this network. You'll notice that despite the fact that there is an edge from 2 to 0, it may not be used to get from 0 to 2, because they only travel in one direction. Anybody who's ever driven around Hamilton should be well familiar with the concept of one-way streets. Directed graphs are, of course, permitted to have cycles, although it's somewhat more difficult to set up a cycle inside of a directed graph than an undirected graph, because you don't just get them for free if there's a loop. The arrows all have to be in the correct direction as well for a cycle to exist. So, for example, let me see if there's an example here. Yes. So, if we consider 6, 7, and 9 here, right, these do not constitute a cycle, right? Because if you start at 6, or if you start at 7, you can go to 6, then you can go to 9, but you cannot return to 7, right? Not even if you follow some kind of fancy path, right? It's not possible to return to 7, so that does not constitute a cycle. Make sense? Hopefully. Directed graphs have an almost identical API. It only has one additional method, which is reverse. So, with our most of the difference between the API is we're now loading slightly different intent on the add edge method. So rather than the edge being just, there is an edge between these two nodes, it is now the first one very much points to the second one, right? And the reverse of a digraph will be the same graph, but with all of the nodes reversed, or all of the edges reversed. So, if we bring back our old friend, the adjacency list, it's instructive at this point to compare the adjacency list for a directed graph to the same for an undirected. Get out of here. To the same for an undirected graph. So, one thing that should be noted, in an undirected graph, when we have an edge between 3 and 2, in the adjacency list, if we follow 3, we will find 2, and if we follow 2, we will find 3, right? So, if we pull the adjacent nodes of 2, 3 turns up from the adjacency array. And if we do the same for 3, 2 will show up. But in a directed graph, if we have, for example, in this case 2 and 3 is bidirectional, so it doesn't work. If we have 2 and 4, right, polling the adjacent vertices of 4, right, yields 3 and 2. 3 and 2. Polling the adjacent vertices of 2 yields 0 and 3. 0 and 3. 4 is not in the list, right? So, when you're talking about a directed graph, the adjacency list is all of those nodes which the node you're talking about points to, and none of the nodes which are pointing to the node you're concerned about. Another way of saying this is that all of the redundancies, all of the redundant pairs inside of the adjacency list have been removed. With me so far? Hopefully. Good. So, you can study the Java implementations on your own time. So, depth first search in digraphs, same method as for undirected graphs. So let's talk briefly about how we go about applying the depth first search to a directed graph. Right? So First, I've said it a few times, but now we have it officially from the official source. Every undirected graph is a digraph, a directed graph, with edges in both directions. Depth first search is, in fact, a digraph algorithm. So, here you have depth first search for an undirected graph. Here you have depth first search for a directed graph. You'll notice that the only difference here, literally the only difference, is this assignment of the edge to matrix, or the edge to array. Other than that, the structure is precisely and exactly the same, minus some curly braces. So, searching in a digraph example. Let's take this other slightly modified, well, actually, I think it's the, is it the same one? No. No, there's something else going on this F. Let me see here. Comparing it. Yes. Yeah, 8 is now connecting to 7. So it's a different graph. This is fine. So, again, we're going to start our search at 0. We take 0. We look up the adjacent edges. It's 5 and 1. So we find 5. And we find, we then look 5 up to see what its adjacent edges are. Right? We find 4. We mark that. Now we're processing 4. We find 3 and 2, right? 3, there we go. Mark it. 2, there we go. Mark it. Nothing left to add to the graph, so we finish. Why don't we need the edge to array? Well, okay, fair enough. Let me just finish this example, and then we'll answer your question. So, depth first search on 2 finishes there, and then we're done. We're done with that branch, so we backtrack, backtrack, backtrack. We then head down the other outgoing branch from 0. We find 1, we mark 1, and that's done. So the depth first search, starting at 0, only finds nodes between it only finds this group of nodes here. Because there is no way for like there are no edges traveling from the left-hand side of the graph to the right. So there's no way that that is found via depth first search, which is an interesting result. So let's talk, let's see, why don't we need the edge to array? Good. So, in the first place, let's remind ourselves what the purpose of the edge to array was in the first place. The edge to array is a parent link representation of a tree rooted at S that contains all the vertices connected to S. We term this tree as an output tree. So this seems like it would be a very useful thing to be maintaining in the digraph version as well. Yeah, I'm not sure why they wouldn't include that, to be honest with you. It seems like an eminently useful thing to have. Yeah. I'm going to go out on a limb and say that this, like, figure 2, depth first search for directed graphs, it would be useful to also keep track of edge 2, because that, like, that's your output tree, you know? The output tree is useful. If you don't need it, I suppose, fine, but, you know, otherwise, how are you keeping track of the output, right? But yeah, anyway. So yeah, any further questions? Cool. Really, really the only thing, my only ambition is that I should take stuff that is confusing and try to make it, try to force it to make sense for you guys. That's like, this is my whole, this is the reason for my existence, insofar as this is the reason for my, professional existence anyways. I have other reasons I exist other than working my job, but insofar as, the work that I do for a living is important in any way, it's like, take stuff that's confusing and try to make it less confusing so people can understand it. All right, I'll talk to you guys later. See you next week. Yep. Oh, also assignment 3 is posted. Bye.